Or when you give them a knife to it.
I mean, that's
part of it. But now that's part of it. So now we're more of
no, it's nothing to worry about. It's just something you have to get through.
Yeah.
And it sucks for the hour you're doing it, but for that's once you get through it, then it's all good times.
Good morning.
Good morning.
How are we doing? So that third practice problem, that life table, I spent an hour trying to solve that life table with the data that was given and could not. So that was all pulled from Dr. Lackey's homeworks he used to assign for this class. I think there was something that he did not include in those notes that he gave them, because I had every textbook out I have that has life tables in it and could not figure out how to solve it. So there's.
But make it worth 0 points, so therefore, if you're higher up pass, you put it on the test.
So there is no higher up that cares about that, so we're good. It's me. Yeah, I'm as high as it goes, evidently, which is kind of, it's scary personally for me as a professional, but yeah. So that won't, basically nothing like that is going to appear on your test. Now we're gonna jump into this idea of mark recapture and the application of mark recapture for managing wildlife population. And mark recapture is one method to estimate a population. And why do we care about estimating populations? Well, if you look at trying to determine the growth rate of a population using the R, instantaneous R, and the slope of the curves, we need multiple estimates of the population in time to determine if it's growing or shrinking and at what rate. So there has been a lot of work within the wildlife science field, ecology field, looking at methods that are both cost effective, time effective, and minimal impacts on the animals or species that you're trying to estimate. So depending on how you set up the study to get an estimate, you can either estimate the actual density of the population in a given area, right? So you have a defined area that you're sampling, or you're trying to look at the overall population as best you can. So you don't have an actual area, you're just looking at trying to see how many animals are out there as best you can tell. So that may occur in, in the state, right? So you can take that. Most of our state agencies manage at boundaries, right? Those boundaries mean nothing to the animals or species, but they do have a defined area. However, because we know that the animals both leave that area and come into the area, you can't say it's an actual density because you don't actually know the amount of space you're sampling. Unfortunately, this method usually requires a lot of time and effort to both initially catch and mark individuals, but then to try to recapture them. Because usually you are marking them in some manner, shape, or form, and we'll go over the types of marking. Many of them are rather disrupting. And certain methods, because of what you're doing to, say, capture them, can also be disrupting. If you are actually putting them in a trap, handling them, putting a marker on them, that all adds stress to the animals. It creates a psychological awareness of what those traps mean in terms of if you go inside of a trap, this is what happens to you. So there are methods that reduce that. There are marking techniques that reduce that. But if you are studying a species or trying to understand the dynamics of a species, you have to have some kind of understanding of what your technique you're using to mark them, how that's going to alter their behavior in the future as you're trying to recapture them. Okay. So what are the three main techniques? Well, they fall into one of the classes. of either natural, non-invasive, or incredibly invasive. So and this is kind of right in the scale of probably how disruptive it is and changing of that animal's behavior, least to most. Natural is you're kind of using the appearance of the animal. The animal has its own pattern, structure to it that allows you to differentiate from every other animal in the population. We use this with things like jaguars and tigers and bobcats that have patterns. Whales have patterns on them that are pretty darn distinctive to those individuals. And we then can use those patterns as saying, okay, we don't have to put a tag in it. That animal itself, because of the way it looks, is providing its own tag. And there's actual computer programs that have algorithms that will run through and actually sort them out for you. So it has created this both easy way of marking and also an easy way of dealing with the data you collect. Non-invasive, so non-invasive can be, trying to think of the best example. Well, let's go to the other end of the spectrum, right? So let's go to invasive, which is highly disruptive in many ways, or can be highly disruptive. Usually involves some type of actual handling of the animal, some kind of capture method to get your hands on the animal, and then the actual marking of the animal can include things that are permanently in place, like tattoos, ear tags, collars, and so on. Generally, to capture, though, things can be, we're about to catch elk with a rocket net shot out of a helicopter. So the helicopter chases an elk around on a mine, flies down to about 5 feet over its head, and shoots a net over top of it while it's running 40 miles an hour. We would call that invasive. Okay. Other examples could include things like rocket nets, clover traps, box traps. Rocket net is kind of like what it sounds, where you're actually shooting a rocket over top of an animal that is attached to a net. So the net gets pulled over top of it. It's loud, it's bright, it's incredibly traumatizing. So that's kind of the two extremes. The non-invasive can be something where you may not actually be catching the animal, but you can mark it. So we have traps where the animal will walk into an enclosed area. There's food in the enclosed area, and they potentially go under a paint roller, and that paint roller puts a mark on that animal. That would be considered non-invasive because they got food, they got touched in a way, but not enough that would actually cause a change in behavior. All right, so it's basically an extreme. You can do the same thing with like a paintball gun. Other methods, powder. They have these colored powders that they can walk through and mark. It's just a way of somewhat identifying.
Tagging marine life from a boat.
Well, in what manner?
Well, not pulling the said animal onto the boat before tagging it. Just
So like the
already
suction
it's
cup.
already swimming in the water.
So like the suction cup things that they do, they
Uh,
pull up next to the animal and stick the suction cup on.
that, or sometimes they'll pierce the dorsal fin, but
So you're piercing the animal. So
so
that's
that would
kind
be-
of
that
where,
would be
yeah, potentially, right? So it all depends on, and some of these are kind of species specific in terms of how they deal with that interaction. So you can pretty much catch a coyote, hold it by a pole, flip it around, and it won't like you, but it'll run away fine. You can tattoo it, put an ear tag in it, put a collar on it, and it will be just fine. If you did that with a deer, it would die before you even get a chance to let it out of the pole.
oh,
So it just depends. So as with all models, and so when I say model, do you all have the statistics courses that you guys have taken? Do you guys talk about modeling? So you guys probably hear the word model quite a bit in classes. How would you define that? What is a model? You make models every day in your head and predictions, right? That's basically a model. You're taking data in and you're trying to make a prediction about either what's going to happen or what did happen. So when we say a model, it's basically an equation of some kind that is trying to explain a system or something in the side of the system. And a model is never 100% correct because it's just trying to approximate what's going on. It's only as good as the data that's used to create it. And they all operate under assumptions. And the assumptions kind of help you understand how valid the model is. Because if you start violating assumptions, then there's a lot of questions about whether that model is correct. It's not accounting for certain things because you can only do so much in an equation. So we spend a lot of time with graduate students talking about models and creating models, how to create models, and they're all usually mathematical models to explain variations in systems and understand what is the best or most influential factors within said system. So we have this mark recapture model, sets of models, there's lots of them, that all have these overall assumptions. Now, you can create new models within this suite that can deal with things that fall under assumptions. So you can basically alter assumptions if your math can account for them. So the basics assumptions of a simple mark recapture model are that you have just as much of a likelihood of catching any individual in that population or area as any other one, regardless of their age, sex, or if they've been marked previously. So if they've been captured. And that part is really important because if your model, which these models all depend on that number of recaptured animals, if you mark animals and don't recapture them because that mark alters their behavior or the event of marking alters their behavior, you violate the assumption of the model and it's null and void. I can tell you right now, we violate assumptions all the damn time in wildlife because it's really hard to meet these. Now we have a good gauge on how over time you can gauge. So certain methods, you know, for like mice and Sherman traps, which is this little box trap that they run into. We know certain species don't react to those traps like others after they've been caught. So overall, you have a like 96% chance of catching a small mammal again if you use a Sherman trap. Okay. Certain species of mice have a higher chance of being recaught than like, so Parameciscus, our white-footed mouse, deer mouse, have a really good recapture rate. House mice seem to be much more traumatized by the experience and are less likely to be recaught. And we can estimate that if we put a tracking device on the animal to know it's alive and just not willing to go back and track. So the ability to recapture an animal a second time is just as important for this model. The other thing is this idea of closure. So for simple models, it's really important. So you do not have an animal either born or immigrate into the system while you're actually trying to estimate the population. Why? So you guys know the population model. You all did really well on it. What are the other components that we're not talking about here?
Deaths and immigration.
Okay, so why is that not in here?
There's a pretty good chance that your animal could actually die.
The animal could die, right? So why do we not care about it? There are models that have to have a assumption of complete survival while you're catching the animals. There are advanced models that do that. But why in a simple mod do we not care when we're trying to estimate a population? You're trying to estimate a population at the end of capture. Why do you not care if the animal's dead or left?
Is it maybe because you're assuming that the same amount of animals are going to be born or enter the?
Nope. Not that guess. So if you're trying to estimate population at the second capture time, so at the end, if an animal dies or leaves, could it be potentially in that population study? It's dead. It's not there, right? So the map doesn't really care if it is dead or leaves because it's no longer in existence. And it's okay because the way we calculate it, it just doesn't matter. It's no longer a number that can be included. If you keep adding to the population, then the math is not able to deal with the fact you are going to drastically overestimate the population than if it dies or it leaves. So it's only as good as the assumption. Now, how many populations don't have animals coming or going?
Next to none.
Yes, exactly. So it's all about that capture time period. And that's how we deal with the assumption is you keep your trapping periods very close together. We do care that the animals that are marked have the same probability of dying or leaving as those that are unmarked. That's what matters. And then this important part, where if you put a mark on an animal, you have to have certainty that's still going to exist. Otherwise, it's kind of acting like you have a birth or an immigration in the math. Okay. So what kind of category would this fall into in terms of marking, you think? Invasive?
Not invasive. I was just thinking because they captured it.
They captured it, they're handling it. So this probably falls in between the non-invasive and invasive section. Invasive, who agrees invasive? Yes, yeah, right. So this animal is now bearing a weight on top of what it originally was carrying. The concerns with this is not that it's carrying more weight, it's now pink, right? It can be seen potentially. So all of which is a concern when you mark animals, because this could go against that assumption. If you're putting a mark on the animal and all of a sudden it can get seen and eaten easier, that causes that assumption to fail. Yes.
Well, obviously with deer, it's a little bit different, but with something like a lizard, why don't they mark like their bellies where they can't be seen? Is it because the paint would rub off or?
So that is because of potential manners of resighting them or recatching them. So one of the things you can do with lizards is you can walk a transect. And if you see the lizard, you can get an ID on the lizard, you have a much more effective mathematically recapture for the model. So if you mark on the belly, it gets a little harder. Also, the belly probably has a little bit lower retention rate. All right. So then we got Scott over here. He's got a deer in Nebraska. High, low, invasive, natural, not natural, obviously. So I can tell you right now, that thing was called a rocket net and it probably died a week later.
It looks like it's invasive considering its tongue's hanging out.
Well, that deer is completely immobilized. So it's knocked out cold. Which kind of goes to offset some of the experience it has. We hope that some of the drugs that we use actually we hope there's a memory issue of the event, so that they can't remember everything that went on.
You're hoping it causes amnesia.
In some ways, yes. And
But you don't know.
well, I've caught a lot of deer multiple times in a rocket net. And I can't imagine if they remembered the event, why they would walk in front of a rocket net again. Because it is not fun.
So how would you determine if your mark is causing something like increased predation or making it harder for the animal to survive? What kind of study did you conduct to even determine that?
So how could we determine if our mark is having impact on survival or even movement, right? Reality being, it's probably multiple projects, multiple questions. You can try to, so a lot of animals can be marked in many methods. And that's one step you can do. So like, how else do we mark lizards? You know, have you guys, so you've done some salamander stuff, right? With duck price. How do you mark salamander? With, so you can use a pit tag, right? What's another method? Yeah, so that's a dye, right? So that's basically what this is. They can tattoo, which is basically this. Okay.
They pull scales.
They can pull scales. You can cut toes. Mark shells. So what generally happens is you're using multiple methods at once and you're looking at, with enough numbers and sample size, you can look at how one mark differs in survival, recapture, retention over time. That's usually how it's done. Because if you try to do it with an unmarked animal, understanding if that unmarked animal is the same animal and what its survival is and movement is very difficult. Yeah. So we try to throw a whole bunch of different techniques out and look at which one seems to be the best. Or multiple techniques combined with each other, pit tag and dye, or tattoo and ear tag, and see which one holds on. All right. So do we understand what a model is and an assumption? Okay. So the simple, probably the initial mark recapture model is this Peterson estimate, or Licken-Peterson is sometimes called. And this is actually supposed to be this like N hat, which is an estimated population, but I couldn't find that in my symbols in PowerPoint, so just bear with me there. So it basically is a 2-occasion trapping event. So you have first time you trap, you mark animals, and the second time you trap, you record the number of marked versus unmarked animals you capture. Okay. And that, when you take it, you have your number of marked animals, the total of the second capture. So we're going to walk through an example. The total of second capture, you multiply them together and you divide by the number of animals you recapture. Pretty straightforward. Yes.
Is the second supposed to be lowercase?
Yes. It is. So lowercase f. I get it down there too. I will fix that and post that up on so it doesn't easy. So this is very basic and it's a real good quick snapshot. However, it doesn't do a great job of dealing with recapture rate issues, and it requires a few things we're going to get into here in a second. Mostly associated with how many recaptures you're able to get based on the number of marked animals you have in the population. So if it's sensitive to the number of marked animals you have. So if you don't catch a lot of animals in terms of percentage of the population, you are going to drastically overestimate the number of animals in the population. So they quickly realized this, and the way this works in general in science is someone will propose a model, show it's effective in some manner, shape, or form, and then people will start using it and finding issues with it, and then they'll alter the model to deal with those issues. So The next step we have from that is this Bailey's model, which is kind of to address that overestimation. So we have this n hat is equal to the number of animals captured the first time, marked animals, times the total of the second capture plus 1. This kind of offsets some of the animals that are caught or that are not caught the first time, divided by the little m down here, the recapture number, plus 1. So it brings that overestimation down just a bit. Not perfect. It helps, though, to address any behavior changes from those that are caught initially. So they're less likely to be recaptured. Or if your number of marked individuals are not at a high enough percentage. For the Peterson estimate to be somewhat accurate, you need to mark in the initial capture at least about 50 to 60% of your animals. That's very difficult to do in one capture event for most species. But so, as with math in general and a model, it's an estimate of what's going on. And estimates really are only good as the variation and understanding the variation or confidence you have in them. So you guys go over confidence intervals, standard deviation, standard errors, and statistics. Okay. What is a standard deviation? What's a standard error? Standard error is easier. Oh, it's that kind of, should I turn the light back on? It's really dark today. There's all kind of falling asleep. Sorry. That person that makes you wake up. So what is a standard deviation? What do you think a standard deviation is? Guesses. Parker.
I knew it somehow. How far away the data will move away from the mean? How far it will be from the mean, I guess.
Kind of. You're kind of right. So, Rachel?
Does it have to like observe versus expected? Where you observe like what you would expect, like standard?
The yes and no.
Okay.
So you have multiple measurements that give you like that you take and you average them together to give you a mean, right? So eight markers, one right there. Thank you. So if we average these together, we get a number. Based on these numbers, do you think your standard deviation, which is Parker, as you said, what was it?
How far it deviates from the mean?
How far what deviates from the data? So each individual measurement, right? So it gives you a gauge on how wide your individual samples deviate from mean, which is correct. Thank you. So why it's important is it gives you an understanding of the variation that exists in your sample. So in here, this is pretty all, they're all kind of tight. Now, what happens if your last two are something like this? You just had a really small standard deviation get blown up into a giant one. Now, what's standard error?
The amount of air you're willing to accept before you throw out a deer. Right, no. It's been a while for me.
Well, let's look at the, we'll come back to that. All right. So The reason I bring up standard deviation, standard errors, because they're basically a measure of variation of your data from the mean, and standard error is basically a measure of accuracy in your estimate. And why standard error matters is because we use standard error in many cases under a lot of models to calculate our confidence interval. So how much trust do we have in our estimate? So in our N hat here, our population estimate. And how we calculate the confidence interval is basically you take this right here, which is under a normal distribution to get 95% confidence interval, you use 1.96. For this class, that's all you need to care about. In statistics, they have an entire chart that you follow. Do you guys remember this? Do you do this?
I remember this.
Yes, that entire thing. And that's all based on a normal distribution. How many types of distributions did you guys cover? Probably just the normal distribution, which never happens. So, but for the basics of math, it's really easy to assume a normal distribution for this, and we will. So n hat plus or minus, so you're getting an upper and a lower limit of your population based on your error in your estimate. So it's 1.96. We're going to walk through an example of this. So you follow that, it gets really confusing very quickly. All right. So we'll walk through it. Now, let's walk through all the things we've covered so far in terms of models. Here is our capture. We went out, caught cottontail rabbits. What's the scientific name of cottontail rabbit? Very good. So our initial capture period and our recapture period, they're 5 days apart. So that we don't violate our assumption of animals giving birth or leaving, or immigrating.
Will you need to remember all of the efficiencies?
So on Canvas, and what will be given to you during your test is an equation sheet. I brought it to lab, but everyone left before I got there. So, because you all are going to get hundreds on the next lab exam because you know them so well. Yes? No. Yes, I hope. Not no. So yes, you will have all of these in front of you. I will make sure you have them. I do not expect you to memorize them. You will have to kind of know when to apply them. But like, it won't just be that standard error. It'll say standard error. It'll n hat equals plus minus to get the confidence interval. That'll all be it. Okay. So given this, we want to estimate how many rabbits we have. So n hat is equal to number marked times the number caught in the second capture period, right? Divided by the number caught in the second period that were marked. You guys notice something with these numbers? And it's true to life here. Why is that 50 when we caught 52? It's really simple. No,
Two of them died when we threw them.
that or they got away. This is a first year technician problem. You actually catch that many, but you're only able to get tags on that many. Well, yeah, so or they die, so you can actually catch.
Or you only bought 50 tags.
Or you only brought 50 tags. I guess that could be a problem too. Given this, and the way the math works out is you get a number a little over 90. General rule for us is you can't have 0.47 of a rabbit. So you have 91. Now, if we throw that, yes.
Hypothetically, what happens if during the first capture period that you keep getting to the same one? So you like catch it and then you mark it, you let it go, and then you go to your next trap, and it's like 3 traps down the line, it's the one that you already caught.
So one of the assumptions is you would not recatch that animal during the same time period. So you would not include that as a, yeah. It could happen, for sure, in certain situations, but you would not include it. Yeah, you wouldn't just keep recounting it. Yeah.
I know you include them in the calculations, but yeah, would you even include the two that got away in your table?
No. So since they're not, well, yes, right? See, this is true to form. This is not unusual. Like, we catch animals all the time and they get away. Like, we would call it the undergraduate experience number sometimes, right? Somebody was supposed to hold the mouse bit them, they threw it up in the air. Yeah, that happens a lot. I have done it. Bulls hurt and they cause you to react. Snakes, people grab the snake turns around, bites them and or tries to strike at them, they let it go, right? So this is a common thing. It happens. We have deer that are in a trap. We get up to the trap and deer actually busts a hole through the netting and gets out. It was caught technically, right? So you would report that, but the big thing to think about is that's not the number that matters, right? Only matters how many catch and mark. Right, so if you incorporate that adjustment, right? So the thought is that we're probably overestimating here. And hat with the adjustment, you get a slightly smaller population, right? Do you think that's meaningful? Is 88.6 rabbits different than 90.47 rabbits if you're managing the population? Yes?
Well, that's like a significant portion of the numbers that small.
What is significant? Define significant.
Well, then you have to run an ANOVA table and all that jazz, but I'm just saying that if you catch 50 animals and then
So
one gives you 50 and one gives you 55, those 5 animals are significant to that population, but if you have a 5 animal difference and you're in the thousands, it's not a significant difference.
thank you for taking the bait. So the point I was going to make, and you're not wrong. Your procedure is to get at statistical significance. You run a test to see if the populations are statistically different by numbers. Biologically, if we're managing this population and care if it's growing or shrinking. If I took this, walk over here, and I am looking at the track of this population over time, right? Say we only vary by 1.5 rabbits over time each way. So you get to 90, 88. The next year, the estimate is, so it's rabbits, so it's like 110, and they grow at the same rate. So we're looking at maybe 106. So 90, 88, we're off by a very similar percentage. And then we get to 120, we're at 116. If you were caring about whether this population, as a manager, over 3 years, and you care about whether or not this population, what direction it's going, biologically, if you implement a management strategy, is it going to differ based on these two numbers and at which the direction that population is going? So that's biological significance versus statistical significance. Statistically, they're not actually different either. You'd have to have a little bit more space, but you can have statistical difference versus biological significance quite often in what we do.
Does that change based on how many litters they have? It's not necessarily litters, but how many offspring they have, because rabbits are going to grow much more significantly but a deer that only has 1 or 2.
See, and we often say deer reproduce like rabbits. So because they grow pretty fast. It's much more important for those that are closer to the K than the R, for sure. And the reality being, though, statistical significance is all about sample size. You can find a difference in almost anything if you have a large enough sample size. Biological significance, it doesn't really matter how big your sample size is as long as you can tell what's going on. And then you figure out if it actually is a meaningful impact to the system. Okay. Does that make sense?
Yeah, that was my question.
Yeah. So it's all about the meaningful impact. Okay. So let's walk through the standard error for move this over here. So I'll put it put it up here for you guys to see it. Or big M is 50. All right. Or what's our U? 38. And our little m. Thank you. Okay. So how does that factor in when we actually calculate this out? Total number of marked individuals. Okay. This is for the Bailey's adjustment. So 39, so that's at 38 plus 1. 38 minus 0.1, 22 squared, multiplied by 23. Are we good? We follow that. We good? Okay, so reality, because it's for Bailey's. Where else do we put plus 1? You can do the same thing for the Peterson, right? Same idea, except you get rid of that plus 1 component. So this would be 21 instead of 22. Okay, it's still, you still add that there. Looks like, yeah, n plus 1. Oh, I'm sorry. No, so that wasn't the Peterson. I'm so confused. Yeah, not Peterson, n plus 1. So you take your number, you multiply that by your standard error, and it gives you your confidence interval. So there's a 95% chance, statistically, based on the data we have, that our population falls between 65 and 113 individuals. So how this would work is if you caught more animals recapture wise, or you have more animals in general, your accuracy is going to get better towards that error, right? So how much confidence you have in your estimate improves. This number shrinks, and your actual population estimate, that range will also shrink. So you have more confidence in what you actually have. Now, 95% is just, you can change that to another number, right? So say you only need 80% confidence in what you want to know. That would change this number here, what you're multiplying by, based on the table. We good? Now, throw this all out the window, because no, we don't do that. The problem here with these two methods are, what happens if you don't catch a high enough percent of individuals that first time? You have some guess of what the population is, but remember, to be effective, we have to get that 50 to 60% marked. So what happens if you only catch 20% of the population, or potentially what the population is, the first time? Well, you can keep marking animals. The problem is you potentially violate some of those assumptions. What are the assumptions that you'd violate if you keep catching? A, it takes more time, right? So your chances of animals giving birth increases depending on the species, and you potentially have more animals coming into the system just because of time. So you get concerns about closure.
And probability of capturing the same individual.
Well,
Start to be.
hold on.
Okay.
There is someone has said that, well, this is a great idea. Why don't we make it so the math works where we can keep catching animals as many times as we need to get a really high percentage of marked situations? Because the Schnabel method here basically was looking at adding like one more time frame or potentially two. Shoemaker and Eismeyer decided that let's keep going. Let's go past 3 because this is probably going to be needed for a lot of our species that we're monitoring. It is still holding the assumption, and this is where it gets harder to keep that assumption, that the population is closed. So we're more likely to violate that. Almost guaranteed in certain situations. Does that mean we throw the entire method out the window if we do violate it? No, it still gives us an estimate. It's a better estimate than we used to have. It's just, you kind of understand that there's something else going on in the system that may change your numbers, and it would require future investigations to estimate that impact of, say, births or immigration on the numbers. So it just leads to more work. Yes.
So if you don't know the population, how do you know when you have enough animals? Just
That's the problem, right? So things that would be concerning. So here's the 2 differences in between the Schnabel and Shoemaker Eisenmeyer in terms of calculations. Right? So remember that this is sum. All of the combinations of CT. So captures in that sample event times the total marked number of individuals in that sample event. So this could be capture event 4 times marked numbers of individuals captured in event 4. You sum all these together and you divide it by the sum of all the recaptures collected in each of the sampling events plus 1. You guys love reading math equations, don't you? They're fun. The variation here, the real big change, is you get a squaring here, and then you're incorporating the number down here. You're multiplying that by RT instead of plus 1. So that's the number of marked individuals during that sampling event is added there instead of just that summing the sampling event. Okay. How does that play out in real life? Well, here's an example of a species, and just insert any species you want. First capture, the way this is laid out, so you have the number of animals caught in that time event, number of recaptures, number of new animals caught, and the total number of tags that exist in the landscape. With the assumption, right, so this should keep going up, the assumption that there's no mortality. So these would sum together. So it starts out, you catch 32, you have 0 recaptures because this is the first event. So you tag 32 animals. You had 0 animals available for capture. Second capture, you catch 54 animals, 18 of those were marked. So if you take this number of marked population, divide it by that, does that get you to 50%? No. Okay. So we aren't really getting a good accurate estimate. So you have to mark 36 new animals. You had 32 available at that point in time to be determined and found. So 36 plus 32 gives you that number. So it's just this plus this equals that. Okay. That continues on. You plug and chug down here with, so this is the Schnabels, right? Of all the recaptures. There, you're multiplying out all the events, and you get to an estimate of 92.81. There is a confidence interval you can calculate for this. It is ridiculously cumbersome and long and drawn out and impossible to do by hand for you all in the time given. It can be done, but you don't have to worry about it. Just know that it exists. So did we have enough, right? We kind of said no. %34.7%. Okay. So the problems and the things you need to take away from this, the nice thing about the Peterson estimate is it's simple, straightforward. It's able to generally meet the closure requirements and the assumptions. However, if you aren't able to catch a lot of animals and mark a lot of animals of the population, it gets a little shaky. So by adding more capture events, you tend to be able to mark more animals, but you have a hard time meeting your closure assumption. So it's this, what do you think is going to work better? All of these are basically not applied or used anymore in current management strategies. They are the baseline for the models we use now, and everything has grown from them. Okay. But all those issues about immigration, emigration, survival, mortality, you can calculate all of those rates, and we can estimate all those rates based on other math that we've developed. So what we've done, instead of just saying, oh, we'll keep it simple and come up with a number, why would we want to keep it simple if we can come up with a better population estimate by including all of those other variables? It gives us a better understanding of the population. So we have all these other models that start to do that. And we're using the new models now, which generally get taught to biologists in grad school because they mathematically get very complicated. But they do exist, and all of them kind of deal with all the assumptions that generally get violated. So like I said, when something goes wrong, an assumption gets violated, we come up with a new math model to deal with that violation to keep it as statistically valid as possible. But all of them are generally adding a new estimate or a new parameter, which is a component we're modeling, to them. So it gets more and more complex. So know that these are important. They're the basics and the building blocks for everything we're using now mathematically to manage wildlife populations. You should be able to do a simple estimate of a population, even at this point in your career. But you should also be able to point to where the flaws are if you go about that. Like we think we're violating this, this, and this because our trapping intervals were 3 weeks apart, and there's a chance that the rabbits could have left the area. We could have had new rabbits be born in the population, so on and so forth. Okay. Questions? Yes.
So could you do like multiple different methods and then average out the results?
It is very common with populations to implement multiple estimates of what's going on. Or in the case that we talked about earlier, use many indices to determine the trend. Yeah, we have a lot of information. Why would you not take that information in and try to interpret what's going on? And we do that. We're not trying to ignore. Now, if something is not valid or there's a lot of questions associated with it, then you don't necessarily put a lot of weight on it. Okay. Yep. So
Shoemaker and estimator slide.
that one.
One for that one. Thanks, and then yeah, chance to write all those down.
This is already up on Canvas, by the way.
Oh wait,
Yeah, I posted it before we came down here because I've got meetings this afternoon.
okay.
All right, so you will be given these kind of things on that sheet. You will have to know how to implement them. All right, so you should expect to get something that looks like this. And I will say, use this formula to calculate this estimate. And based on this trend, you know, what is your management strategy for this situation? Or I could say, this is your estimate year one, we implemented this strategy. 5 years later, we reevaluated the population, and this is what's going on. Is this population doing well? Is it not doing well? Should we go back to what we were doing before or not? Okay. Good. All right. That's all I have. You guys have a wonderful weekend. Oh, enjoy your fall break, right? So we don't have class Tuesday, no lab. Thursday, we're gonna get into a different population estimation technique because Kate is going to do her wildlife disease lecture the Tuesday, the 2nd, the election day, because I evidently do not have childcare, so I don't think you want to see my 3-year-old running around in the halls. So, yeah. Yeah, no, she could be a terror. Yeah. I brought my oldest in here when she was 3, and she sat down here and colored and was like happy-go-lucky the entire lecture. My youngest does not do that. No.
My little sister's 3, and she's a little terrorist herself.
Yeah, they are something. They can be. Every child is its own.
Have a good weekend.
You too.
All right, see you later.
See ya, Ethan.